Hey, hi, how are ya? Let's do some math. All right. This is fundamental theorem of calculus part 2 day. We have learned the fundamental theorem of calculus part 1 in our last lesson. Today is all about doing the second one. All right, normally in this lesson for warm up, I actually have two examples, this one and this one. Two examples of free response, like released free response questions from old AP exams, where graphs are given and they're asking you to find areas underneath the curve and stuff like that. So these are going to be great questions to come back to together in class, but for the sake of the video, we're going to jump to the lesson. Okay, so we're gonna talk about fundamental theorem of calculus 2. We're going to build up to it like we did FTC part 1. And we're going to start by figuring out the sum, or the area underneath the curve, the exact area underneath the curve of x squared and 2x plus 1. Okay, so let's do this. I'm going to start off by saying this, though. I'm going to go ahead and let capital F of x, and I don't know why they choose capital F, because it looks a lot like lowercase f, so it kind of freaks us out, but capital F of x, we're going to let be equivalent to 0 to x of f of t dt. So we're going to let f capital X, or capital F of x, be the area underneath the curve of f, okay, from 0 to x. So it is that integral. Okay. All right. Let's start by doing number one. Let's start by doing the Riemann sum, and I'm going to do this pretty quick because we should be pretty good experts at this by now. I'm going to say the limit as n approaches infinity. We got b minus a over n, or 7 over n, summation I equals 1 to n, and then it's a plus b minus a over ni, and I'm going to go ahead and plug that into x squared. So that's actually just going to be 7 over ni quantity squared. Okay. Now, take your time and solve this one out. For the sake of the video and for the sake of space, I'm going to go ahead and really kind of jump down a few steps here. Okay. If I were to take out the 49, if I were to take out the 49 n squared, all right, times 7, I really have 7 cubed on the outside and n cubed on the outside. And I'm left with the summation of I squared, which is n plus 1 to n plus 1 over 6. Okay. And if I take that limit, right, on top I have, I'll do this in blue. On top I have 7n, n, and 2n. So that's going to be 2, 7 cubed, n cubed. And on bottom I have 6n cubed as the leading terms. So my area is just 2 times 7 cubed over 6, which when plugged in the calculator is 343 over 3 units squared. Okay, so that's the area underneath the curve from 0 to 7 of x squared. And that's using the definition of Riemann sum. Okay. Now we're going to bring back what we talked about at the end of class yesterday. This is going to lead into FTC part 2. F of x is x squared, right? Okay. What would be capital F of x? Or, what we talked about yesterday, what would be the integral of x squared? Well, we've already made the connection with FTC part 1 that it's just the antiderivative of x squared, or working backwards from it. And we learned how to do that with x squared yesterday. In fact, I think we did that exact one. It's 1/3 x cubed. Okay. 1/3 x cubed. Now, that's the integral of x squared. So now let's figure out capital F of 7. So what happens if I plug 7 into that? That's 1/3 7 cubed. And what happens if I plug 0 into that? That is 1/3 0 cubed, or just 0. And then what happens if I were to subtract those two? What happens if I do this operation here? It would be 7 cubed over 3 minus 0, which if you do this in the calculator is 343 over 3. And if you compare that to doing the definition of an integral, you're going to notice that it's the same exact thing. Very, very interesting. So what that means is if I take the integral and I plug the upper bound and subtract the lower bound, it gives me the same exact area. So there's your shortcut. Let's verify it again. Let's try it over here with this one. Okay, so we can do the long way, and we'll do it really quick. I'm gonna really kind of just simplify this out a little bit. The setup is the limit as n approaches infinity of b minus a over n, or 9 over n, summation I equals 1 to n, and I'm going to go ahead and plug in a plus b minus a over n I in for x. So that's 2 times 1 plus 9 over n I in for x plus 1. Okay. I'm really going to jump the gun here. I'll do a couple steps, I guess. So we got the limit, n approaches infinity. I'll go ahead and just simplify out the summation. If I distribute the 2 and add the 1, that's 3 plus 18 over ni. Okay. Which I can separate. Okay, which I can separate to this. Okay. I can take the 3 out, so I got 27 over n summation of 1 plus, and I can take the 18 over n out, which is 18 times 9 is 162 over n squared, and I'm left with the summation of just I. Okay. So we can keep going. I mean, I'll do the limit part real quick. Okay, so I'll go ahead and try to squeeze it in right here. But this is all review, right, guys? This is all review. That's 27 over n. The summation of 1 is just n. And this is plus 162 over n squared. And then remember, the summation of I is n plus 1 over 2. And I'm really squeezing it in there. That ends up being 27 plus, and that ends up being 162 over 2, or 81, which is 108. Okay, I'm sorry that I crammed it all in there, but we've done this countless times. The area underneath the curve of 2x plus 1 from 1 to 10 is 108. Now, that's the long way. Let's think about the new way. This is actually leading into FTC part 2. So what if I found the actual integral, capital F of x? What if I found the actual integral of this? What if I work backwards? Well, 2x is really x squared, and 1 is x. That's working backwards from integrals. The derivative of x squared is 2x, and the derivative of x is 1. If I plug 10 into that, that's 10 squared plus 10, which is just 110. And if I plug 1 into that, that's 1 plus 1, which is 2. And if I take that difference, I get 108. So that's leading to something here. It means taking the integral, or finding the area underneath the curve between 2 points, is just finding the antiderivative and subtracting the upper bound, subtract the lower bound. Huh? So using that information, let's figure out this one. Using this information, we're going to figure out the integral from -2 to 3 of x cubed dx, which means not doing the whole long definition anymore. We can do the shortcut. We just learned that if I did capital F of 3 minus capital F of -2, I'll have the area underneath the curve. So first off, capital F of x is the integral of that, right? Which we add 1 to the power and divide. It's 1/4 x to the 4th. So to figure out the area underneath the curve, I'm going to plug 3 into that. And I'm going to subtract plugging -2 into that. Okay. Now, for sake of time and argument here, this fraction ends up becoming 65 over 4, and that is a lot less steps than having to do the actual area underneath the curve formula. All right. And that's what FTC part 1 or part 2 is. is capital F of the upper bound minus the capital F of the lower bound. So let's kind of have a slide that describes all that. So it says let capital F of x be the antiderivative of f of x. So working backwards. Then, okay, the integral or the area underneath the curve of f from a to b is just equal to the antiderivative of b minus the antiderivative of a. And that statement right there, that is FTC part 2. And that is where our shortcut rules and quick math comes into play. This is also known as the net change. And in context, especially when you were seeing this with chart problems with velocity, all right, if we let velocity be the rate of change and s of t is the distance, then the integral from a to b of our velocity, or the area underneath our velocity, is just equal to the position at b minus the position at a. The change in displacement from time equals a to time equals b. Okay? So, for instance, just a little word problem here. If v of t is equal to this, inches in feet per second, then the integral from 0 to 5 of v of t simply means that we would that would give you the distance traveled in feet from 0 to 5 seconds. Okay. From 0 to 5 seconds. So that's where the context comes in. That's where that relationship between area underneath the curve to antiderivatives. Let's look at some word problems, just understanding how to interpret these. It says, write a sentence to answer each of the questions. So, okay, if h of t is the rate of change of the height of pile of a sand measured in feet per hour, okay, so h of t pretty much says how fast the height of a pile of sand is changing per hour. Well, then what does the integral 0 to 5 of h of t dt represent? I'll give you a second, maybe pause the video, maybe try to write that out if you want. But integrals of a derivative, all right, of a rate of change, if you take the integration of a rate of change or the area underneath the curve, it's an accumulation problem, right? So what this means is this is the change in the height, the accumulation of height. So we're going to say the change in height, the change of height of sand in feet from 0 to 5 hours. This tells me how much sand has accumulated from 0 to 5 hours. That's another way you can say it. The amount of sand accumulated in height, the height accumulated in feet from 0 to 5 hours. What about number 2? If v of t is the velocity, so we got a rate of change here, moving along the x-axis, measured in feet per second, what is the integral from 3 to 10 of v of t represent? Okay. Well, that's working backwards to position function. So it's an accumulation again. So this is telling us the distance traveled in feet from 3 to 10 seconds. So from the 3rd second to the 10th second, it is telling us how far we have traveled. It's an accumulation. What about this one? If b of t is the rate of growth of the number of bacteria in a dish measured in bacteria per hour, what does the integration from 2 to 6 of that rate of change represent? So the area underneath the curve of a rate of change, the antiderivative is like the amount function. So this is an accumulation, right? So this is talking about the rate of change of the growth. So this simply is just saying the accumulation or the amount of bacteria grown from this hours, yeah, 2 to 6 hours. And then lastly, if P of t is the rate of growth, well, sorry, yeah, okay. If P of t is the rate of growth of a rabbit population measured in rabbits per year, and there were 100 rabbits in the year 2005, time equals 0, write an integral expression that represents the rabbit population in 2007. Okay, this is kind of working the other way now. I'm giving you a description. Okay, P of t is the rate of growth of the rabbit population. And I want you to write an expression that tells me the amount I'm going to have in the year 2007. Okay. This is a specific formula. And I'm sure you can figure it out if you pause the video and try. But the amount of rabbits between 2005 and 2007, how many I'm going to have, is always equal to the initial, so the initial amount, plus how much I've accumulated over the amount of time. So the accumulated amount over given time. So simply put, the initial amount in 2005 is I got 100 rabbits. I'm going to add to my initial amount the amount of rabbits that I've accumulated from time equals 0 to 2007. So that's 2 years that have passed. So that's from 0 to 2. So I'm going to take my initial amount plus the amount that I've accumulated from time equals 0 to time equals 2. And it's just of the function P of t dt. Okay. All right, let's keep going. Now these are 4 multiple choice type of problems. I think these are good problems. I'm going to quickly go through them. This is the rate of change of the altitude, so the change in the height of a hot air balloon is given by this. This is a rate of change problem. T cubed minus 4t squared plus 6. And we're looking between 0 to 8. Which of the following expression gives the change in altitude of the hot air balloon during the altitude when it's decreasing? When it's decreasing. Okay. Okay. So this is a calc-active problem, and I can't really show you the calculator, unfortunately. But this is not asking about the change in distance over the entire interval. This is asking about the change in distance when this is decreasing. So unfortunately, I can't really show this. What you need to do is take this function, it's t cubed minus 4t squared plus 6, and you need to figure out on that calculator, on that graph, where this is negative. Because think back to how derivatives describe functions. If you can figure out where that is negative, that is where the function is decreasing. And that's the interval that we're curious about. That's going to give you your upper and lower bound. So I'm telling you now, if you were to graph this and look where the function is negative to figure out where your original function is decreasing, that is between time equals 1.572 and time equals 3.514. Okay? So the one that correctly identifies that, it's either going to be it's not going to be this one or this one or this one. It's between A and D. Well, it's always the integral of the rate of change. So it's not the rate of change prime. It's just the rate of change. So it's this one. Okay. So you can try to find these values on your own and try these problems. And I encourage you to try these other problems before I do it. Pause the video and try them on your own. All right, here number 2 says a particle moves along the x-axis so that at any time t greater than 0, its acceleration is given by this bad boy. If the velocity of the particle is at 2 at time equals 1, then what is the velocity of the particle at time equals 2? Okay. Okay. How do we do this problem? Well, we have the acceleration, and it wants to know the accumulated velocity. So if I have the derivative working backwards, taking the integral, or the area underneath the curve of acceleration, will tell me the accumulated velocity, all right, which is what it's asking for at time equals 2. So this is how it works. You start off with your initial value. We're starting off at time equals 1, it's 2. So I'm going to put 2 plus. And then you're going to, so if I want to know, okay, so if I have my velocity at time equals 1 to be 2, if I want to know it at time equals 2, I need to know what my accumulation of velocity has changed from 1 to 2. So how you do that is you're going to write the integral from 1 to 2 of my acceleration function. Which you have to do a little bit of math here. This is going to be equal to 2 plus. And if I were to take the integral of this, the integral of this is actually, I'll write it right here, capital F of x. It's a couple power rules. So if we add a power, it becomes a square, and divide by 2 becomes 5.11x squared minus 14.775. That would be the x. That would be the antiderivative. Because if you take that derivative, you're left with what you're starting. So this will be equivalent to doing capital F of 2 minus capital F of 1. Okay. And I'll let you write that out and let you try that on your own. But if you were to correctly do this, talk about the 2 plus the accumulated velocity, you'd be left with C. And then number 3, let g be the function given by, okay, it's an integral. So g is an integral between -1 and 3. On which interval is g decreasing? Okay. Go back to your justification. G is decreasing when g prime of x is negative. So why not take the derivative of this and figure out when it's negative? So by FTC part 1, g prime of x is equal to, we're taking the derivative of an integral. We know from yesterday's lesson, that's just going to be what we started with, sine of x squared. And if you were to graph this function on your calculator, this is calc active, and look to see where it's negative between 1 and 3, that interval ends up being between 1.772 and 2.507. And in class, we can show this on the calculator later. But for now, these are just some good application problems. And then lastly, it says if f is the antiderivative of this, f is the antiderivative of this. So f is equal to the integral of this, such that f of 1 equals 5, then f of 4 equals what? So if I were to take the integral of this over a specific amount of time, it shows me how much I've changed, how much have I accumulated from one time to the other. So anytime I want to know a new value, I need to have an initial place to start. So think about this. At a value of, maybe think of it as time equals 1, I'm at a position of 5. So initially, okay, my initial value is 5. If I want to know a new value, I need to add the accumulation, which that comes from an integral. So if I want to know my new value at 4, for instance, you're going to add the accumulation from time equals 1 to time equals 4 to figure out your new value. You take your initial and you add your accumulation, which in this case, the function was 0.06205x squared minus 0.264x plus 0.351. For sake of time, I'll let you try that on your own, but try taking the antiderivative of this, all right, while plugging 4 into it and then plugging 1 into it and subtracting it and then add 5 to it. Okay. It ends up being D. But see if you can take the integral, like add 1 and divide, add 1 to the power and divide, and try to, it'll be a cubic, plug 4 in, plug 1 in, subtract, and then add 5. Okay. We can definitely, in class, solve any of these problems by hand, but for the sake of video, I'm trying to get through all of the slides. Okay. All right, and I only have one more slide to go over. Now, it's 3 new problems. Honestly, I would be okay with you just going ahead. You can cross out number 8 because we literally did that as our last example in yesterday's notes. So I got 3 examples I want to do before we're done, and I got 4 minutes to do them before 30 minutes. Okay, look. These 3 problems are really what I want you to take away from today's lesson. This is the big takeaway from today's lesson, is understanding how FTC Part 2 works. FTC Part 2 says don't do Riemann sum anymore. Don't do that long formula. You can just do capital F of your upper, or I'll just call that B, F of B minus capital F of A. And that will tell you the area underneath the curve between 2 points. So for instance, this right here. Okay, I'm going to teach you a new notation too. If I were to take the integral of this, the integral of x cubed is 1/4 x to the 4th. Add 1 power and divide. So I took the integral of it. Now it wants me to evaluate the integral from -2 to 1. This is a notation thing with integrals. It means once you take the integral, once you find the antiderivative, the notation is you put a line beside it, and this is your bounds. It tells you to find the area between -2 and 1. So literally all you have to do is 1/4 1 to the 4th minus 1/4 -2 to the 4th, which equals 1/4 minus 16/4, or simply -15/4. Let's try this next one. The only integrals we know how to take the integral of right now are polynomials. So let's make sure we rewrite this as 2x plus x to the 6. Distributing that will make our lives easy. Now, the correct antiderivative of 2x is x squared. And the correct antiderivative of x to the 6 is if I add a power and divide, it's going to be 1/7 x to the 7th. And we're evaluating this from 0 to 2. So all you got to do is simply plug 2 into it. So we're going to be 2 squared plus 1/7 2 to the 7th. And then minus plugging 0 into it, which is 0 squared plus 1/7 0 to the 7th. And I did this in the calculator, but this goes to 0, and this simplifies down to 1/56/7. Okay. And then lastly, this is a good one. I almost don't want to do it and see if you can do it on your own. Stop the dang video and try that one on your own. It's not a polynomial, so you can't do it. But I'm taking the integral of secant squared. Remember what an integral is. It's the antiderivative. So you got to think, is there any derivative out there that equals secant squared? Can I take the derivative of something that gives me secant squared? Yes. Okay. The derivative of tan gives me secant squared. So that means if I take the integral of secant squared, I'm back to tan. So this is equal to the tan. All right, the tan of t evaluated from 0 to pi over 4. We're going to plug in pi over 4. And we're going to subtract plugging in 0. Tan of pi over 4 is 1. Tan of 0 is 0. This equals 1. So the area underneath the curve of secant squared from 0 to pi over 4 is 1. And I'm 10 minutes away from 30 minutes. Can you believe I finished it? I rushed a little bit. So try it on your own, and we'll try to finish tomorrow in class.